Good morning. We discuss now what is carrier diffusion. First of all, we'll discuss the diffusion process. We have considered the drift current, that is the transport of carriers when an electric field is applied. Another important current component that can exist if there is a spatial variation of carrier concentration in the semiconductor material. The carriers tend to move from a region of high concentration to a region of low concentration. This is called the diffusion current. To understand the diffusion process, let us assume an electron density that varies in the x direction. The semiconductor is at uniform temperature so that the average thermal energy of electrons does not vary with x. Only the density Nx varies. Thus, we consider the number of electrons crossing the plane at x is equal to 0 per unit time. Because of finite temperature, the electrons have random thermal motion with a thermal velocity V thermal and a mean free path L, and we know that L is equal to the product of the thermal velocity and the mean free time, that is tau c. The electrons at x equal to minus L, the mean free path away from the left side, have equal chances of moving left or right. In a mean free time tau c, one half of them will move across the plane at x equal to 0. The average rate of electron flow per unit area F1 of electrons crossing the plane x equal to 0 from the left is then given by the equation F1 is equal to half n into minus L into L divided by tau c. This gives the value half n into minus L into V thermal. Similarly, the average rate of electron flow per unit area F2 of electrons at x equal to L crossing the plane at x equal to 0 from the right is F2 is equal to half NL into V thermal, as you have shown in the equation over here. The net rate of flow from left to right can now be given by the difference of F1 and F2. So F becomes equal to F1 minus F2, that is equal to half of V thermal into N into minus L minus NL. So, approximating the densities at x is equal to plus minus L by the first two terms of a Taylor series expansion, we obtain F is equal to half of V thermal in brackets N in brackets 0 minus L dN by dx minus in brackets N0 plus L dN by dx bracket close. So, this gives us, as you have shown in the equation, V thermal L dN by dx, which is equal to minus dN into dN by dx, where capital Dn, as you have shown in the equation, this is equal to the diffusion coefficient. This is also called the diffusivity, because each electron carries a charge of minus q. The carrier flow gives rise to a current. This current Jn is equal to minus qf, which is given by q capital Dn into dN by dx. The diffusion current is proportional to the spatial derivative of the electron density. The diffusion current results from a random thermal motion of carriers in a concentration gradient. For an electron density that increases with x, the gradient is positive and the electrons will diffuse towards the negative x direction. The current is positive and flows in a direction opposite to that electrons, as we have indicated in the figure as we have shown over here. So, if the current is flowing in the positive x direction, electrons will be flowing in the negative direction. Here we have shown a graph of electron concentration versus distance. L is the mean free path. The direction of electrons and current flows are indicated by arrows. So, here this is N, which is a function of minus L, and here L is a function of L, here N at the position 0. This is the graph of electron concentration versus distance, where L is the mean free path, the direction of electrons as you mentioned earlier, and the current are indicated by arrows. Thank you.